Hi again, and welcome back to ViViMaT. Our next speaker, Krishnanand Shukla, is currently wrapping up his PhD at the National HIPIMS Technology Centre at Sheffield Hallam University in the UK. He develops hard and functional coatings using industrially sized PVD systems that are equipped with HIPIMS technology. During his PhD work, he and his team developed a new method to efficiently plasma nitride steels and alloys. Before starting his PhD, he worked at ISM at the University of Bordeaux, where he developed a microporous coating on a miniaturized electrode with potential application as a biofuel cell. Over to you, Krishna. Coatings is a peer-reviewed journal of coatings and surface engineering published online by MDPI on a monthly basis.
And now, magnetransferring.
Hello all. Thank you for attending this talk, and I would like to thank the organizing team for inviting me to give a presentation on one of my work, which title as Dry Sliding Wear Mechanism of HIPIMS Plasma Nitrided CoCrMo alloy for Medical Implant Application. HIPIMS technique was originally developed and industrialized at Sheffield Hallam University, and this full form of the HIPIMS is high impulse magnetransferring, and where the power is applied on the target in a pulse mode. The reason why I'm focusing only on CoCrMo alloy is that my whole PhD is focused on the biomedical application, where I'm using CoCrMo alloy to surface modify and then further to analyze in a different medium to prove that whether the HIPIMS plasma nitride can be better use than compared to the commercial DC plasma nitriding. So why we need plasma nitriding? So imagine we have an alloy which has hardness from 450 to 550 HV, and then if we are doing any application point of where the load bearing capacities need to be very high, and in that situation this can be very soft. So ideally in industry they do plasma nitriding, which is basically a chamber. Inside the chamber there is a plane surface which acts as a substrate holder, and this substrate holder acts as a cathode as well. So you apply potential, negative potential at your substrate and positive as a chamber, and then you generate plasma DC discharge on it, and plasma nitriding happens. But plasma nitriding itself is not proven to be effective, so it needed more. So functional coatings are another option, which can increase the hardness from 1500 HV to almost 33 HV. And so after this two system, it forms a gradient, hardness gradient or stress gradient, which makes this alloy more suitable for the application than originally without any coatings. So in this work, I'm going to only focus the plasma nitriding side of the treatment, as well as its application in dry sliding conditions. So now here I'm not talking about the tribo corrosion side, but only the pin on disc dry condition wear mechanism. So my objective of this talk is to understand the dry sliding wear mechanism of the untreated CoCrMo alloy, which is still not known, and understand the effect of nitriding voltage, because we have changed the nitriding voltage from minus 700 to minus 1100 volt, and to see how the microstructure as well as the layer composition changes. So yes, here so I will be also discussing about the effect of nitriding voltage on wear and friction coefficient of cobalt-chrome alloy, and further my objective here is to understand the oxide formation on the wear track and the damages uh, below the nitrided layer or within the nitrided layer. And at last, I'll be discussing about the correlation between the oxide layer and the phase and chemical composition through Raman and XRD analysis. So this is what nitrided layer looks after HIPIMS discharge used. So the first is 700 volt, where other parameter we are keeping the same, such as base pressure, which is -3, 8.3 10 to -3 millibar, and nitriding voltage, which is 400 degrees Celsius, and power on during the whole experiment is managed to fix at 1 to 2 kilowatt. And you can see here for the 700 volt we had two distinct interface, which is one, the thick one is the gray, which is known as compound layer, and has chemical microstructure, chemical composition of cobalt-2,3 nitride and cobalt-4 nitride. And there is another, the fine line of diffusion layer, which is, you can say, he has a white line layer, and it's very thin, somewhere around 100 to 150 nanometer, and it has a structure of cobalt-4 nitride. The B, which is 900 volt, and here we can see that both the layer thickness changed, and now the diffusion layer is thicker than 700 volt. And later in C and D, you can see this 1100 volt diffusion layer disappears, and the compound layer still get bigger and bigger. So the maximum thickness which we received achieved here was around 5 micron, depend on where we are measuring, and lowest was 1.3 micron. So as I said, my main objective to first understand the wear and frictional behavior of the untreated cobalt-chrome alloy. So here we can see the cobalt-chrome alloy when it was not nitrided, how it behaves. So starting 500 kilometer, 0.5 kilometer, it was very much clean. We can see the less disturbance, only the friction coefficient is increasing. At some point it start stabilizing, and then as soon as the sliding distance increase, the presence of oxide, the debris can be seen because the waviness in the friction coefficient values. And then further 1 kilometer and 2 kilometer, this behavior changes drastically, and we can see that 1 kilometer we had a very big unsteady state region, where it shows that there is a formation of various oxides, base islands and all. And in 2 kilometer, after after around 1100 meter, it start again stabilizing and very steady state region shows, and this defines that at some point the oxides start stabilizing and press into the layer, which we can visualize through the SEM imaging. And here we can say the A, which is 500 meter or 0.5 kilometer, we can say is pretty much clean, except grooves, which is expected from literature. In case of 0.75 kilometer, it's still pretty much clean with minor formation of oxides. And then in 500 kilometer, these grooves were deeper, deposition of the islands were bigger and flat, and then in case of 2 kilometer, very thick oxide sorry uh, the very thick oxide layers were formed, and this defines that the CoCrMo alloy at some point start making its own oxide based protective layer, and these protective layers thickness can vary from 0.3 micron to 1.2 micron, and here is the transformation of this oxide layer. So A is when it was 0.75 kilometer, B is when it was 1 kilometer, and C is when it was 2 kilometer. 400 meter, the sliding running period was visible for 700 900 volt, whereas for the 1000 1100 volt it was almost zero, which means it start directly at higher and then start stabilizing at some point after running for 50 to 20 to 50 meter. And most of these waviness represents the damages happens during the sliding of the surface, because one of the reason is that these two samples have high roughness as well as their microstructure in a way that they can break if the high voltage high load is applied. Same goes for the 2 kilometer. It has similar behavior. Starting 400 meter had very much waviness, and then later it starts stabilizing, which means these 2 body and 3 body wear is getting minimum here. In terms of values, which we can see here, is that table 2, that thickness of this layer was every time was increasing by times of 2, and then friction value was highest for 700 volt, which I already said, because we can speculate from in this running period how it increase and then start stabilizing. But in case of 2 kilometer, it was because it's average, so we found that it's somewhere 0.6, and but in case of 1000, the average was almost 0.59, which means with increase in bias voltage, the average friction value decreases. And it same goes for the wear coefficient as well, and we can see that for the 700 and 900 volt it was very low, and then it start increasing for 1000 1100 volt. The SCM surface analysis is basically depicts the same what the value says, and we can see that 700 900 volt surface was hardly damaged when it compares to the 1000 1100 volt. In 700 and 900 mostly they were grooves, and these grooves were filled with the debris. And where in case of 1000 1100 volt, some of places there were a lot of chunk of the layer was removed. We can say plowing behavior was there, and why I'm saying at higher magnification, we can see that now here is the same thing which I said for the low magnification. So here we can see that the grooves are wider and deeper with the increase in bias voltage, as well as the sections of the nitrided layers are removed in many places. And same goes for 2 kilometer case, and we can see that after running for 2 kilometer, the thin layer of oxide or nitro oxides are formed, but in case of 1000 and 1100 volt, the center of the wear track is heavily damaged, due to the three-body via. And subsurface analysis confirms the idea of three-body via, because we can see the C and D, how they are damaging the layer as well as the substrate, and the cracks within the layer is also defined that due to the high load as well as the long sliding distance, one possible crack formation can be shearing, shear stress based cracks, and as well as in some cases it was fatigue as well. And here we can see that the F, E, and F as well as D. This is basically 1000 and 1100 volt, where the most of these cracks are within the nitrided layer and are flowing deeper inside the substrate, which shows that these shear cracks as well fatigue cracks are not good for the application point of view. And but in case of A and B, where this is just 709 volt, no cracks were found within the layer below. In case of A, the pit or the hole which we see is basically not a crack due to the tribo, but it was due to the inclusion which is pre-exist within the cast alloys, cobalt chrome cast alloys. And at last we perform the XRD and Raman on the samples, and we found that the Raman spectra for all these samples were the same, where the mostly chrome oxide and molybdenum oxide are varying based on the thickness as well as the point to point. Whereas in case of XRD, we found that in untreated case, cobalt based oxides are a main constituent as well as the contributing more, whereas in other case the cobalt based oxide start disappearing, and mostly these oxides are dominated by the chromium and molybdenum, which is similar to that of Raman. In conclusion, I would like to say that the wear resistance of the untreated CoCrMo alloy increases with increase in the sliding distance, and in case of nitrided specimen, the best wear and friction combination we found for the 900 volt, which had the lowest wear coefficient, which 1.11 into 10 to minus 15, with the nano hardness of 23 GPa, and this hardness is almost 1 to 2 times harder than that of the commercially available nitrided specimen. And in case of worn surfaces, we found that chromium and molybdenum are the main contributing oxides when we analyze the oxide layers, and same goes for the XRD, except the untreated alloy had cobalt based oxide present. And I would like to acknowledge my all team for supporting me to finish this work, as well as my funding agency Zimmer Biomed for sponsoring my PhD. Thank you.